welcome to Friday's edition of Cracking the Cryptic, and a puzzle that has been described by some people as their favourite puzzle ever. And, well, it might be my most, well, it's certainly very, very colourful, absolutely beautiful. It's called Serial Killers, and it's by starwarigami. And this one, I think, has got some maths in it, to be honest. I've read the instructions, which are very short, and we're definitely going to have to do some thinking about arithmetic to even make a start on this. But I love the fact that it's sort of, how many colours have we got? We've got five colours. So we're going to be working on the 5-colour theorem today, and we will have a look at this. This puzzle, by the way, has 5 stars out of 5 for difficulty on Logic Masters Germany. I did just check, and I think a 99% approval rating. So it's obviously brilliant, but it's probably difficult as well. You'll be able to judge better than I will by the video length, assuming I've managed to solve it at all. But, I mean, we are in an absolutely purple patch, a purple patch of puzzles. The last couple of days, I have been absolutely in awe. This, I loved yesterday. It's called Hopscotch Remix by Nordy. Absolutely beautiful idea. And that came right on the back of this one, the Easter Miracle, the completely blank grid. So if you haven't checked out either of those puzzles yet, do have a look at them. I'm sure you will like them. They're really, really quite remarkable. Now, what else can I tell you about? We've got a bonus video on the channel today. We're continuing our series of spending our Friday mornings doing the Times crossword. Friday is normally the hardest day of the week in the Times. So if you want to improve your cryptic crossword solving, that video might be for you. Next, I've got a birthday to announce. A very happy birthday to Dave, all the way over there in Kentucky. Dave, I know you've turned 34 today, and your wife Laura wrote to us, and she said some really lovely things about you. She said she's so proud of you as a husband and father to your 5-year-old, and that's lovely to hear. So Dave, I hope that you have a brilliant birthday, and maybe your 5-year-old might enjoy something we've got coming up, I think tomorrow on Patreon, which is our Super Mario Brothers sort of Sudoku hunt. And the idea is that this should be appropriate to get your kids into Sudoku variants. Something that you can do with them and sort of get them involved. I hope it's not too difficult. I think we'll have lots of older kids who can just zip through it. But for younger kids, they probably will need an adult to hold their hands, and hopefully they'll catch the Sudoku bug. So look out for that tomorrow. And then, for more experienced solvers, should we say, of variant Sudoku, our Knightmare on Sudoku Street hunt has been going great guns. Let me show you the front page of that from the Sudoku Skunkworks. Absolutely brilliant puzzle hunt. 19 puzzles in that altogether, and the following people have solved all 19. So very well done to Niels T. Natterstad, Megan Swanson, Nathan Cox, John Andrew McCulloch, Kimberly, Dr. G, Zorro, Jose Cusco, Charlie Skyra, Vincent Vermau, Joe Chang, Olimar, Triple Three Ears, I never know how to pronounce that one, Chris Mears, Matthew Brockwell, Kaz Burton, C373S, and Grufty. So some slightly unusual names today, but all fantastic solvers, one and all. And with that said, let's have a look. Serial Killers by starwarigami. I've done starwarigami puzzles before, and my recollection is they're always wonderful. And these are the rules of this one. Normal Sudoku rules apply. Digits may not repeat in a cage. Okay, so that's telling us that digit cannot be in either of those 2 squares. Normal Sudoku obviously would stop this digit appearing in those 3 squares, but this digit also cannot appear in those 2 squares. The totals of individual cages of the same colour form a set of consecutive numbers in any order. So, right, let's start let's start with green then, just to talk about what I understand that to mean. Is that this cage, let's say this cage added up to 12, then this cage could add up to 13 and this cage could add up to 14. But in some order, those three cages have to sum, or no, those three cages individually have a sum. Oh, this is hard to explain. Yeah, the totals for the cages have to form a sequence, a consecutive sequence, but that sequence could be in any order. So if that was 12, that could be 14 and that could be 13, or that could be 14, that could be 13, that could be 12. But in some order, if these cages individually summed up to 12, 13 and 14, that would be a legitimate sequence for those three cages, because it would form a consecutive sequence overall. That is literally all the information you get. So you get so let's think about red for a moment. So red, how many cages have we got in red? 1, 2, 3, 4, 5, 6, 7. So the cage totals here have to form a sequence of 7 different numbers. So it could be, we've got some 2-cell cages in there. So it could be 7, 8, 9, 7, 8, 9, 10, 11, 12, 13. They could be the totals for each red cage. But we wouldn't know if it was those digits. We wouldn't know, you know, the 7 could be up there and 13 could be next to it. We don't know how the cage totals are disposed within the red region. So I suspect we're going to need to avail ourselves of some secrets to solve this, but do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. Now, I'm tempted. I can tell you something immediately about that cell. That cell is 3, 6 or 9, and that might seem like sort of witchcraft to some people that I know this is 3, 6, 9, but it's not at all. That just derives from 2 little nuggets of information that I already know. One of those is a secret though, and don't worry, I will tell you the secret, because if you're watching this video, you're definitely one of my favourite people, but just keep it to yourself. Now the secret is that any complete box of a Sudoku, indeed any complete row, any complete column of a Sudoku, because of the rules of Sudoku, contains the digits 1 to 9 once each. So I know what the total of all the digits in that box is. It's 45. That's the sum of the digits 1 to 9. But I also know something about 3 cages, or 3 consecutive numbers, I should say. Because if we think about 3 consecutive numbers, let's say that the middle-sized number there, we're going to define that as x. Then the lower number will be x minus 1, and the higher number will be x plus 1. And if you sum those 3 numbers, you get 3x. Now 3x is therefore divisible by 3, so I know that these 8 numbers are divisible by 3, and I know that 45 is divisible by 3. So how can those two things be the same? Well, only if this number itself is also divisible by 3. So that has to be 3, 6 or 9. And, no, well, I can't quite perform the same trick here. We can do an inversion of that logic here, can't we? We know that purple overall must be divisible by 3. And we know those squares are divisible by 3. So we know that those 2 cells summed together are divisible by 3, which is a slightly more tricky deduction. One, 2, 3, 4, 5, 6. There are 6 cages in yellow, which is not... That doesn't feel like something terribly useful. 6 cages in yellow. So what maths can we do on yellow? We can say that if the lowest value cage in yellow, we'll define that as x, then the sequence will be x, x plus 1, x plus 2, x plus 3, x plus 4, and x plus 5, won't it? Is that right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yes. So that will sum up to 6x plus 15. So 6x plus 15 is divisible by 3. Well, that's not surprising, because actually I could have seen that a different way, couldn't I? Because those two boxes together must add up to 90, because they're going to be two lots of 45. But I know those two are divisible by 3. 90 is divisible by 3, so I already knew these were divisible by 3. So 6x plus 15. How is that in any way helpful? I don't know. Okay. Okay, have we got... The thing is, I think where you've got these enormous numbers of cages, I suspect the maths just gets more and more complicated. How many did this have? 1, 2, 3, 4, 5, 6, 7. There are 7 in red. So that's going to be 7x plus 21, isn't it? Using sort of the logic of the lowest digit being x, and then adding 1 to each of those digits. So that's going to, this adds to 7x plus 21 altogether. And I don't know if that matters, but the interesting thing about that having an odd number of cages in it is that one cage is going to be the average. It's going to be the exact middle of the sequence, isn't it? So if it were, what did I say before? 7, 8. So if 7 was the lowest, 7, 8, 9, then the 10 would be the middle of the sequence. There's got to be a cage in red that adds up to at least 15, because that's a 5-cell cage, and the triangular number for 5 is 15, i.e. what's 1 plus 2 plus 3 plus 4 plus 5? That's got a 15 in it at least. How many cages are there in blue? We've got 1, 2, 3, 4, 5, 6, 7. That's got a 6-cell cage in it. Ah, okay, so this one's got a 6-cell cage and a 2-cell cage, which is interesting, because the 6-cell cage, the triangular number for 6 is 21, but the low, okay, so if that was 21, and what's the lowest this cage could be? 21, 20, 19, 18, 17, 16, 15 would be the lowest that this cage could be. So that's at least that gives us a pencil mark. So the absolute minimum here digit we could put into this cage is a 6, because we need these two cells to add up to at least 15. Obviously they could be 16 or 17, but they must be one of 15, 16 and 17. What did I say this one was? That one was 7 digits, wasn't it? I'm wondering if we can do some sort of massive deduction based around all of these cells together, maybe. Or can I get the value of that one? Right, so blue and red have each got 7 cages, and we know that 7 cages adds to 7x plus 21. So, oh, right, yeah, okay. Well, that's quite interesting. Sorry, I should have spotted this, but I didn't. So 21 is divisible by 7. Yeah, so blue and red are each individually divisible by 7 in total. So, right. So all of those squares together add up to a number that is divisible by 7, because 7x plus 21 is divisible by 7. And we know that, well, I know that those squares add up to 135, so I need something near 135 that's divisible by 7. And 135 is definitely not divisible by 7. No, it's definitely not. 134 is would leave a remainder 60. No, 63 is going to be it, isn't it? So 133 is divisible by 7, and that goes into 133 is, I want to say 19. Goes 19 times. So 7 goes into 133 19 times. So okay, but 133. If this, yeah, okay. So this is a 2 or a 9, isn't it? Because if these added up to 133, but these added up to 135, then the difference is 2. And if I go 7 down from 133, I get 126, and then this would need to be a 9. So this is 2 or 9. Now, if it's 9, that has to be a 7-8 pair, because it has to add up to at least 15. So if that's 9, that has to be 7-8. And that doesn't work. That doesn't work. Right, this is not 9. I've got a digit. I feel like I've been going round the houses here, but I have got a digit. That's not 9. Because the way I got that to be 15 was I made that 21 and then counted down. So that's how it's possible for this domino to add up to as little as 15, is if this adds up to exactly 21. But if that's got a 7-8 pair in it, how do I keep 7 and 8 out of this cage? I can't do it. And the reason, the reason that's important is for this to add up to, for this to add up to 21, this has to be 1, 2, 3, 4, 5, and 6. So it can't have 7s and 8s in it. But by Sudoku, if that's a 7-8 pair, there's nowhere for 7 and 8 to go in this box. You can't make this simultaneously 7 and 8. It won't work. So there would be a 7 or an 8 in there, which means these are too far apart to be in the sequence. So this is wrong. This is wrong. So now what does that mean though? It means this is a 2, because it can't be a 9. I am very tempted to say that that means that's a 2, but I haven't done the maths on that yet. Let me think about this. So now, well, now we can work out the mathematics of blue, can't we? Because we've worked out that yeah, this must be right, because we know blue adds up to 133, and we know there are 7 cages. The average value of a cage is 19, and we worked out that because there are 7 cages, one of these cages has to have that average value. So one of these cages is 19, and that's the middle one. So there's going to be a 19, and then lower than 19 there's going to be an 18, 17, and 16. So 16 is the lowest cage, which means this cage cannot have a 6 in it. Good grief. And it must have a 9 in it, because it's at least 7, 9. So it's either 7, 9 or 8, 9. It's not necessarily the lowest cage. I was about to say it is the lowest cage, but it's not, because if that was 9, 8, one of these other cages, which actually could be many of them, could be the 16 cage. Okay, so there's... Right, so there's 16 cages the minimum, 19 is the average, there's a 20, a 21 and a 22, and that is going to give me a 2 here, surely. Because I've now worked out that this cage, which has a minimum value of 21, has a maximum value of 22. So how could we leave 2 out of this cage? It would then add up to a minimum of 1, 3, 4, 5, 6 and 7. Which by my count is 26, and it's much higher than it should be. So this has to be a 2. And there's all sorts of other digits that have to be in here. This has got to have in it 1, 3, 4. Well, it's got to have, in fact, let's do this. It's got to have in it 1, 3, 4 and 5, and then either 6 or 7 as its final digit. So the 9 in this domino has to go there. This is getting very interesting already. So 9 is up here. And if this was... Yeah, oh, okay, how could that be 9, 8? There's nowhere for the 8 to go in this box then. This is ridiculous. So that has to be 9, 7. Let me get rid of the 9 pencil. It has to be 9, 7. There is a 7 in here now, so there is no 6, because it must therefore be adding up to 22. So this is the high cage in blue. And this is a 6, 8 pair, which is adding up to 14, and we know that what's the minimum? The minimum was 16, which we've got. So this is high. Well, okay, this has got all the options in the world apart from 1, basically. Right. So 2 is in one of those cells. So I've got 22. I've got 16. So I've got 17, 18, 19, 20 and 21 to find in blue. Is that in any way doable? I don't know is the answer. I suspect that there is some jiggery-pokery going on here though. I can't immediately get my head around how to sort that out. No, sorry, I've not got anything. So maybe we're meant to use this too, are we? Because... well, okay, I know that this lot of cells add up to 90. So at the moment, with that one included, we're on 92. But we know red overall has to be divisible by 7. He says, trying to work out what that means. Does that mean that this has to be... I should know this, shouldn't I? I feel like 91 is divisible by 7. 91 is divisible by 7. So 98 must be divisible by 7, which would make this a 6. Let me just check that. 98, 1 is 14, isn't it? So it has to, in fact, it has to be, right, okay, that has to be a 6. Sorry, that's been obvious for ages. It has to be a 6 because we're looking for something that's divisible by 7, and the other options here were only 3 away from each other. So we're not going to find another multiple of 7 that's only 3 away from one that works. So this is a 6. And now we can do the maths on the red region much more precisely, because we know that all of the cells add up to 98, which averaged at 14. So the average value of a red cage is 14. So one of these is 14, and the lowest cage is therefore 13. The lowest cage is 11. That's so brilliant. Look, the lowest cage is 11. And how does that get to even a value of 11? It can only get there if that's a 9. So now there's a 9 in one of these. And we know that red overall is made up of 11, which we found, 12, 13, 14, which is the average, 15, 16, and 17. So 17 is the most. 16, 17 is the highest value. So that can't be a 9. Absolutely no way. Because this, well, this has got to have all sorts of low digits in it. Because the maximum value of that cage is 17, I've just worked out. So those squares either are a 1, 2, 3, 4 quadruple, or they're a 1, 2, 3, 5 quadruple. So they definitely have 1, 2, and 3 in them. And that's definitely not 2. So 6 in this box is in one of these cells. We're going to be able to do some maths on green in a minute as well, but hang on, let's just keep thinking about red for a second or two longer, because I suspect we can do better than this. I've got 11. I know that this one is either 17 or 16. But one of them somewhere has to be 17, because we know the average is 14. It's going to be very hard to keep track of this, because obviously we've got different stuff. Even now I'm trying to think about it. Oh, this one, the lowest was the 16, wasn't it? And the highest was the 22. So this is low 16, high 22. This is low 11. And high 17. And we've got this digit, which is going to tell us the mathematics of green, because now we know that the green cells add up to 39. So the average value of the green cells is 13, which means that these are made up of a 13, a 12, and a 14 cage. And that's about as useful as a chocolate teapot. 13, hang on, 12, 13 and 14. Can we say anything about those? They're distinctly average, aren't they? I don't think so. That digit feels like it's weak to me. I feel like I should be able to write that in. That digit is, from a Sudoku perspective, 1, 3, 4 or 5. It can't be 1, because that would make these add up to 15, so it's 3, 4 or 5. So 1 is over there. Let's record that. That's 3, 4 or 5. There is definitely a 1 over here. Now, if we put 1 into a 3-cell cage, what do they have to add up to? And the answer is at least 17, isn't it? Well, hang on. This cage has to add up to at least 17, because 16 has gone. So if I made that a 1, they have to add up to at least 16. So there needs to be a 9 in there, which there can't be. There we go. So 1 is in the 5-cell cage, which actually... No, okay, I couldn't have necessarily deduced that before this point, but I have now deduced it. What about those 3 digits then? Do they have to have a 1 in them? They can't now be 3, 4, 5, so the minimum they could be would be 3, 4, 6 if there's no 1 in them. That's 13, 22. 22 would be repeated, and that's not going to work. So there is a 1 in one of these squares. I don't think this is doing it, is it? Okay. I don't think we're going to get... What did I work out about purple? Those two have to add up to a multiple of 3. I don't think that's going to be even interesting, I'm afraid. And yellow, 1, 2, 3, 4, 5, 6. Yellow yellow was expressible as 6x plus 15, wasn't it? 6x plus 15. I'm just wondering if there's parity going on there. So do I know? Yeah, okay, there is, isn't there? So if that's 6x plus 15, then I want to say that that cannot be even. It cannot be even, can it? Although those two squares have to be divisible by 3, if they added up to 6, say, so say that was a 1-5 pair, then mathematically we know yellow must be equal to 90 minus 6, which is 84. But we know that 84 has to be expressible as 6x plus 15. But when I deduct 15 from 84, I'm going to get an odd number, and then x will not be an integer. But maybe does x have to be no, x does have to be an integer because that's the lowest cage number. Yeah, so that doesn't work. Okay, so this domino adds up to an odd number that is divisible by 3. So so this is getting more interesting now. So this is either 3, 9, 15, etc., etc. Let me think about that. If that's 3, it's a 1-2 pair. Which, let's do the maths on that. If that's a 1-2 pair, these squares add up to 87. 87 minus 15 is 72. 72 divided by 6 is 12. So this would be 12, 13, 14, 15. 12, 13, 14, 15, 16, 17. Which is fine, isn't it? What's hard about that? 12, 13, 14, 15, 16, 17. There's not enough 2-cell cages, I think, to make that tricky. If these were 3, what's that doing to this one? That's making these add up to 48, which is... So the average value of these cages is 16 then, 48 by 3. And there's got to be a 15, a 16, and a 17 cage. That can't be a 15. Right. You've got to look at this. You've got to look at this downwards. If that's a 1-2 pair, that's got no legitimate value because these purple cages have to be 15, 16, and 17. There's no way to do that. So this is not 1-2. We know it's not adding up to 6, so it's adding up to at least 9. So if these add up to 9, I'm going to check down here now. It might still be difficult, this. If this is 9, this is 54, which averages 18, which means these are a 17, 18, and 19 cage. And that's adding up to 9, so that's at least an 8. Which is fine, isn't it? If that's an 8, wow, it's putting 8 or 9 down here. So the best it does is puts a 9 here, puts a 9 here. Bobbins. Okay. I'm just going to check whether 9 breaks anything here in yellow. If this is 9, my phone's buzzing at me. If this is 9, then we know yellow sums to what? We know that yellow sums to 81, and then we do the adjustment with the 15, which takes us down to 66, which is 11. So the lowest value here is 11. So we've got an 11, 12, 13, 14, 15, 16 cage. Right, but that's at least a 15 cage. So if this is 9, that has to be a 15 or a 16 cage. It would have to have a 2 in it. I'm just wondering if we can actually rule out 15, which is going to be the next legitimate number here. It might be that that gets too small to exist, because what I think I've just worked out is that if this adds up to 9, the maximum value of a yellow cage is 16, but that's adding up to at least 15. So that's got to be a 15 or a 16 cage. But if we increase this further, and we know that this can't add up to 12 because it's got the wrong parity. So if it adds up to 15, then yellow adds up to 75. 75 minus 15 is 60, so x is 10. That's not what I wanted. I thought we were going to lose 2 degrees of freedom, but we're not. So x would be, so the lowest cage would then be 10, 10, 11, 12, 13, 14, 15. Ah, bobbins. All right, so that cage there is a 15 or a 16 cage though, because if we go up again, it's not going to work. This is going to have no value. Let's just double check that then. So if this was 21, which is going to be the next legitimate value, then we've got 69 minus 14 is 55. That doesn't sound right. Have I done the maths wrong there? I think I've just done the maths wrong. That cannot work. 69 minus 15, it's 54. No, 54 is better. That's 9. And then the maximum value of this would be 14, which is too low. Right, so this cage here is either 1, 2, it's definitely got a 2 in it. It's either 1, 2, 3, 4, 5, or 1, 2, 3, 4, 6. So it definitely has a 2 in it. Ah, look. Well, now I've got a quadruple there, but there's definitely a 2 over here. But if there was no 6 in this cage, oh, then I'm not forcing anything into here. No, I don't know whether that digit appears in this cage either. So, no, because if this is a 5, but this is 1, 2, 3, 4, 6, then that digit wouldn't be in here. Okay, sorry. This square is not a 1 because there must be, in this quadruple, the 1 is definitely there, so that's not a 1. So these 3 digits, the remaining digits, have got to be the high digits, haven't they? 7, 8 and 9. That's an 8 then. That's become an 8 because it can't be a 7 or a 9. So now we've got a 7-9 pair down here, and I can't remember what the maths of green was. So the maths of green was averaging 13. So we've got, so one of these is a 9 in a 3-cell cage. That feels like that's going to be quite constrained then, because the maximum we could accompany the 9 with would be 2 cells adding to 5. So if that's 9, we'd get a 1, 2, 3, 4, 5 quintuple in the row. I can't see why that feels like it's wrong, but I can't immediately disprove it. This is 8, so here we've got 17. And what were the values we were looking at in blue? The highest, I remembered this was the highest blue, that's 22. So this has got to add up to a maximum of 21. Right, so that's got to be a 1-3 pair. There we go. Because there's no way it can't be any less than that, and it can't be any more than that from a blue perspective. So this square is not a 3, which means that 3 is down here. These don't include 3. Or 1, actually. So these are from 2, 4, 5, or 6. These squares are from 4, 5, and 6. Three has to be over here somewhere. We've used up... Okay, so we've used 16 up. We've used 21 and 22 up, haven't we? And this one is adding up to either 18 or 19, neither of which has been used up. Bobbins McBobbins face. I doubt that digit can be a 2, actually, looking at this. Because if that's a 2, aren't these going to not add up to enough? Because this I can see has to be quite low. The maximum value of this digit is 5. Let's actually just put that in. 1, 3, 4, or 5. So if that's 5, well, if that's a 2, the maximum value of those two squares is 11, and that's only 13. But we know that we need at least 17 in here, so this is not a 2. So now this cage has a 1, 2, and a 3 in it, which is 6, and the other two digits have to add up. Well, they're going to have to be at least 4 and at least 4 and 7. If there was no 4 in this cage, oh, it's still fine, isn't it? That's absolutely fine. Right, sorry. Can that be a 1? Oh, hang on. I've looked at this pencil mark here and seen that this has a 1, 2, 3 in it, but that could... Why do I think the 1 is over here? Yes, I did that logic. I did do that. That's fair enough. That one pencil mark logic was correct, because remember, if that was a 1, these two had to add up to too much, given they can't be 8 and 9. So that is not a 1. So this is 3, 4, or 5. I've got... Oh, but 3. I've assumed 3's over here as well. That's not correct, is it? Oh, bobbins. Right, okay, we need to check this. Can that be 3? If that's 3, these two have to add up to at least 14. No, it can't be 3, actually. This is great. Well, it's not great, but it's mildly interesting. This can't be 3, because these would have to add up to 14 without using 8 or 9. So that means I've now got a 1, 3 pair in row 3. No 3 in the corner in this box, at least. These two squares, if this was a 4 or a 5, that would give us 9, and we need at least 17, which we couldn't get. So that's a 6. Look at that. That's the world's... Oh, it nearly does it. It nearly rules 6 out of this. But if I could rule 6 into this, that would be far more useful, because then I think I'd know what that had to add up to. Okay, let's work out this digit then. So these 3 digits add up to at least 17. So these add up to at least 11. So that's got to be a 7. That's all it can be. I need these to add up to 11, and this can't be 6, 8, or 9. Well, it can't be 5, because then those won't add up to 11. So that's 7. That doesn't mean I know what this one is, though. Ah! Hang on. If that was a 4... If that's a 4, that's 17. And that's fine. And if it's 5, it's 18. Oh, that's beautiful. What beautiful. That is so clever. Right. That's not 5 for a lovely reason. See, if you can't see why that's the reason, just pause the video, because you'll love it when you spot it. Why can't that be 5? It can't be 5 because it would make these add up to 18. But by this being 5, it makes this 4, and those add up to 18 as well, and we'd have 2 18s in blue. So that's not right. So that must be 4, that must be 5, and now we've got 19 here, but only 17 here. So we've now used up, it's hard to keep track of this, we've used up 16, 17. No, we haven't used up 18, have we? Because this one, now neither of these is 18. So we've still got 18 to find. Then we've got 19. We haven't got 20, but we've got 21 and 22. Right, so these cages have to add up to 18 and 20. And that's become a 4, look, by the power of using this as a 5. Oh, hang on. Can we do some more eliminations down here? Look, 1, 3, 4 triple. I simply don't believe it. It still doesn't do it, does it? A 1, 3, 4 triple. But I already knew there was definitely 1, 2, 3, and 4 in here. So the key digit is whether there's a 5 or a 6 in this cage. And unless I'm mistaken, I don't think I know. I don't know. Okay. So, Alright, let's do something simple then. These can't add up to 16, so this cage can't add up to 20. And the reason these can't add up to 16 is there's a 7 already in the box, and we need a 7-9 pair. So this domino adds up to 14. Oh, I still don't know what it is then. It adds up to 14 though. It's either 5-9 or it's 6-8. Okay. How can that not be resolved? That's so mean. So these have to add up to 20. Oh, I see, and this has just got the other in it, hasn't it? Ah, okay, but... Hang on. Hang on, let me think about this. Maybe this isn't resolved, actually. I'm not sure now. I can't quite get my head around it. This is from 2, 4, and 5. Oh, 4 can't go in here. So is that a 2-5 pair by Sudoku? Sorry, it's unsurprising, but I'm not doing my Sudoku very well in this Sudoku puzzle. So now I've got 4 over there. So this becomes 1. So now, so now you can't put 5 in there, which means that is 6-8. And if that's 6-8, I get to put 9 in the corner. Now I'm just going to check the maths on this. That works. That does add up to 20. I can immediately see it. So that feels like it might matter, doesn't it? And that stops that being very high. Didn't I need, for some version of this, I needed that to be quite a high digit? I can't remember now what that had to be for that to work. That can now only be an 8. I'll put 8 down here. Ah, bobbins. Okay, so what can we do with this knowledge? We've got 7s and 9s here and here. What were the totals here? We've got I've had another thought actually. I can limit this. I don't think that can be an 8. Because where do I put 8 in green? And I don't think I can put it with a 7 or a 9 in a cage, because these cages have to add up to 12, 13 and 14. So if I put 8 in the same cage as a 7 or a 9, I'm immediately blowing the total. So actually in this box 8 is in this domino, which means 8 is in one of these 3 squares, which means 8 is not here. So the highest digit this can now be is 7. It can't be 6 either, you know. But I can't remember what that meant for. It meant something for one of these variations I was looking at over here, but I can't remember which one. We worked out, didn't we, that this was not a 1-2 pair. It wasn't 3, but it could be 9, it could be 15, I think. That's what we worked out. 9 was the one that gave a high digit here, I think, because yes, that's obvious. If this adds up to 9, these add up to 54, so the average value is 18, which means there's a 17, an 18 and a 19 cage in purple. But if they add up to 9, that's got to be at least 8. It now can't be 8 or 9, so that doesn't add up to 9. Therefore it adds up to 15, which means it is 6, 7, 8 or 9. That's not 9, which means that's not 6. And what I can't remember is what that meant for the mathematics of yellow. If this is 15, yellow adds up to 75, which means that 6x plus 15 is 75, which means 6x is 60, which means x is 10. So 10 is the lowest digit in yellow. 10, 11, 12, 13, 14, 15 is the highest, so this hasn't got a 6 in it. Good grief. Good grief. Right, that's not a 4. So this is a 2-5 pair now out of absolutely nowhere. And 6 has to be in this domino. Well, I'm going to actually label these up. 6, 7, 8 and 9. I've now, oh yes, okay, so now I've got a quadruple on 6, 7, 8 and 9 in row 6, and I know something better than that, because those two add up to 15, those two add up to 15, so there's sort of a virtual 15 cage there. Oh, but hang on. Oh, I might have broken this. No, I've broken it. Oh, what? How did I manage to do that? Sorry, I don't think the mathematics of this works. I thought I just worked out that x had to be 10. 10, 11, 12, 13, 14, 15, and therefore that had to be a 15 cage. But then this cage, which seems to have to be populated with 6s... Oh! No, that's fine. Oh my goodness. My brain's gone. It's gone. I've been defeated totally by Star Origami's puzzle. I couldn't see. Isn't that weird? I couldn't see how this could add up to less than 15. That's so strange. Look, it could just be 6 with 7 or 8. It can't have 9 in it, I suppose. That's what we could say. Oh, that's great. That's actually helpful. Oh, no. Okay. I've officially gone completely mad. But I'm quite relieved I went mad, briefly, because it's actually allowed me to resolve this. So now, by Sudoku, that's become a 6-7 pair. How very strange. But that's good, because 6 and 7 definitely don't add up to as much as 15. So now these two squares don't have 6 in them, so they've become a 9-8 pair. Which means this column, look, we haven't put into it 1, 2, 3 and 5. So these digits are, so the 8 is placed down in this box. And we're going to be able to work out some things here, because, unless I'm very much mistaken, we know the approximate values of the green cages, don't we? Because we've got 12, 13 and 14, so that's got to be a 5. It's the only valid way of making a cage total. And that 5 gives me a 5. This is stunning the way this unwinds. Now I've got 1s and 3s in green here. And I've got 4s and 2s into those squares. Oh, but hang on a moment. That square's got to be the same as that square, I want to say. In fact, that's got to be a 4 by the sort of the same logic. This cage, according to my pencil marks, has 1, 2, and 3 in it. So that digit is in the red cage. Well, where does it go? It must go there. So that's got to be a 1 or a 3. But more interesting than that is now this can't be a 2, because it wouldn't have a place to go in red. So that's got to be a 4. That's got to be a 2, and now there is no 4 in there. I can't remember what that meant. Probably something very profound. Well, let's think about that for a second. I think 11. Did we know for sure? Oh, yes, we did. We knew when we were looking at red that red's average value was 14. So the lowest value was 11, wasn't it, which we found. But the highest value, 11, 12, 13, 14, 15. I don't know, 11, 12, 13, 14, 15, 16. The highest value was 17. And we've now discovered that that is the 17. Okay, so, all right. So this is the 17. And we've got the 11. So we've still got to place the 12, 13, 14, 15, and 16. Ugh, horrible. Okay, but there are some things going on, aren't there? Now, that is a 1, 2, 3, 5 quadruple. Add that in, and that's a 1, 2, 3, 4, 5 quintuple. So these squares are from 6, 7, 8, and 9. That square is not 9. That square is not 7. We know they're 15, don't we? So from a maths point of view, we know purple is averaging 20. So there's a 19, 20, and a 21 cage in purple. A 19, 20, and a 21. And those add up to 15. So this is 4, 5, or 6. Sorry, that's been available for ages. It's not 6. There's a 6 looking at it. So it's now 4 or 5. So this is either the 19 or the 20. Don't know. I'm not sure. This domino is very restricted now as well, because that domino sees the whole of the red cage, as well as the 5 and 8 in its row. So what can this be? It can be 4. No, it can't be 6. It can be 7, or no, 9 it can be. 4, 7, or 9. No, that one can't be 9. And what are the values for this? We need this to add up to... okay, it's got a 9 in it, because it needs to add up to more than 11, because we've got the 11 in red already, so that square's a 9. That's not 9. That's done absolutely nothing. Can we eliminate either of the options here then? So this is either adding up to 13 or to 16. And that's dealing with the 17, so no, we can't. So these squares are from 4, 7, 6, and 8. What's the maximum? The maximum is 16. So I've got to be a bit careful with these two. But this square doesn't seem to be restricted. Although, actually, hang on. Maybe I've got to pencil mark this row as well, because I've got this weird quadruple going on, haven't I? So these squares, Mark would be very proud of me for doing this level of pencil marking. But I'm trying to keep track of what feels like a lot of things in my brain, all at the same time. Poor brain. Has that in any way shed any light on anything? Not really. If that was... okay, that square might have to be a bit higher than its minimum value. Because this domino is adding up to at least 12, isn't it? So there's no way that this can be a 4. It just doesn't work. If it's or a 6, if that's a 6, you can't make it high enough. So this is a 7 or an 8 now, and this still needs to be more than 3. So this is 4 or 5. Oh, come on. That's not 6 anymore. Okay, I don't know then. So 6. So this box has now got 6 in it. So if that was a 5, we would be getting up to exactly 17 as a minimum, and 17 is too many because that's a 17. So that's not a 5. So this is down to 1, 3, 4. Oh, have we done it? Not sure. I'm not sure. I don't know. Sorry. I'm sorry if you spotted how to progress from this juncture. 2 I can see is in one of those 3 cells. That might be useful. What are the cages down here? Oh, it was huge, weren't they? 19, 20 and 21. And that, this cage, oh no, okay, if this is 6, 7, it's not that big. It's still got it's got at least 13 in those 2 cells, so these 2 cells cannot add up. Well, they can't include a 7. They could, or a 6, or a 5, so that... so this is restricted down here. I think that's right, isn't it? The maximum cage total in purple is 21. So if that's 6, 7 as a minimum, that's 13. I can't put 8 in there. Can I put 7 then? Oh no, I can't put 7 because this will be minimum of 6, 8, and then the other cell would have to be a 0. Yeah, so these squares here have to be lower than 5, so they've got to be from 1, 2, 3 and 4. Oh, it's so nearly good. That feels like it's got to be. That feels like it's sort of important, doesn't it? But I don't think I can do anything with that. Alright, let's go back. Can I get that digit restricted? I can't remember what yellow was. Yeah, okay, yellow was 15 as its maximum. So that cell, well, it's not really restricted at all. 9 can't definitely, it can't be a 9 in there. Oh, 9, maybe it's 9. 9 can't go here. So 9, okay, 9 in box 4 is in one of those 2 cells, definitely, which means that's not 9. But I can't remember what this is down here. Why have I got 6, 7 and 8 here? Oh, okay. So now 9 is in one of those 2 squares in row 8. Do we know the order of the What were these boxes? We've got a 13, haven't we? 13 was... Ah, that's the average. So one of these is a 12. And one of them's a 14. Well, if we put the 9 here... Oh no, that's okay. Is that okay? 9 and 1 would work. And then that would be a 1, and there'd be a 1 up here. Sorry, I think that's fine. I think I'm just... And if that's 7... yeah, just... bobbins, no, okay, we don't know. I thought maybe I could do something clever then. That was foolish of me. Okay. Oh no. Okay. It is quite tricky to keep track of everything that's going on here. I will confess that. I'm feeling like I'm missing quite a lot, actually. Because each of these colours has its own, you know, its own property. So in yellow now, I've had 13 and I've had 15. And the lowest one we know is a 10, don't we? See, if that didn't have 1 in it, it would be a minimum of 3, 4, 6, which is 13, which I've already had. Okay, so that would be... it still could add up to 14. This digit... I feel like this digit has to be quite low. Let's just think about that. It could be 6, though, I think. It can't be 7. Okay, so that's... No, it can't be 7 for many reasons. So this digit is 1, 2, 3, 4, 5, or 6. Is there any way we can lock that down further? Don't think so. Right, we're now getting to the point where I feel very stuck. Over here, we've got 11. That was the low one, and 17 was the high one. If that's a 7, 4 has to go in the same positions as 6s. But this would add up to 10. So this would be 13 or 14. Which I think is fine. Oh, hang on. Here's a very small point that's quite good actually. That can't be a 4, because then you couldn't put 4 in this box anywhere. So that can't be 4. So this is now 1 or 3. Oh, it's so nearly interesting. Oh, I don't believe it. I don't think I can do anything with that. Okay, well, let's come back to this. Maybe if I can get rid of 1 from here. If that's 1, this has to be... It's got a 6 in it, hasn't it? So then we'd have 7 in 2 digits. I don't know. I'm not quite getting that, I don't think. Or... Sorry. I am trying to do this. I know it probably doesn't look like I am, but I really am trying to do it. Have we got any of the jiggery pokery that we had up there, where you could create? Is it those two? We could create the same total in. That might be something that's worth thinking about. Don't think so. 6 is here, 6 is here, 6 is in one of these 3 cells. Seven. Can that be a 7? That would be an interesting. Oh. Ah, I've only just noticed, look, that 9 is quite restricted here. 9's got to be in one of those squares. So if I put 7 in one of these squares as well, then I'd have 16. And I'm not allowed to beat 21. That's still okay, I think. Right, so we've got, instead of that, we've got to do, what do you think? I don't know. If I could work out, that can't be 9, I've just realised, because of the pencil mark 9. So now I've got down 9 down to one of 2 places. So we're getting there slowly but surely. 7 was in one of 3 places, wasn't it? Probably in this box. Oh, but actually look, wherever the 7 goes, it's going to do some things over here, which I think is also going to unwind my 1s and 3s, because if, for example, that was a 9, I would know this had to be a 1, and then that would have to be a 1. So they would be a minimum of 2, 3. Can we do, it could be Sudoku, you know. There is always that chance. Have I missed some obvious Sudoku-age? Possibly. Oh, I have. Oh, it's unforgivable. Oh, I've missed Sudoku. Oh dear, dear, dear. Right, okay. Well, we'll elide over that part of the video where Simon didn't ask himself, where does 7 go in the bottom row? Because that 7 is ruling itself out of here, and my pencil marks seem to suggest that 7 must go in the corner. So this is an 8 now. Ah, this is going to be massive. Right, okay, this is hugely exciting as well, because that is now a 3. Because we've got 4, 6 here. If this was a 1, it would add up to 11, and that adds up to 11, so that's got to be a 3, which means I've got 13 here, which means this can't be a 5, because that would then add up to 13 as well, so that must be a 4. So this is not a 3 in any sense of the word. This is not a 3. That's not a 3. Okay, has this done it or not? Are we just going to die a death here? I'm not sure, actually. This has become a 1. Okay, so now this is not 1 or 3. This is 2 or 5. We've got a 2, 5 pair in those squares. Oh, come on, this must be. So we've got a 12 cage, we've got a 13 cage, we've got a 16 cage, and a 17, and then an 11. So what we haven't got is a 14 cage and a 15 cage, which is a shame. 14 and 15. Well, I'm going to do some more Sudoku then, because that Sudoku tells me the nature of that cage, which cannot now contain an 8, so cannot possibly add up to 15. So what does that mean? A very good question. In fact, that it means that's an 8 by Sudoku. That's one of the things it means. So surely I can do this column. That square at the top is a 1 or a 5. So I've got a 1, 5 pair. That becomes a 4. That becomes a 4. That becomes a 6. 11, I've forgotten this. 12, 13. That's 16. So I need a 14. Oh, hang on. I might have made a boo-boo here. I think I have. I can't see how to make this work at all. Hang on, hang on. Red, the minimum value of red, I seem to be claiming was an 11 cage. Was that correct, or was that based off nonsense? It was, because I worked out the average value was 14, didn't I, for the reds, I think, because I thought they added up to 98. So 14, 13, 12, 11, which is that one. Now I've got 11, 12, 13. I haven't got 14, but this can't be 14. But I haven't got 15, and this can't be 15 either. Oh no. Oh no, 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 no. So what have I done wrong here? I have not got a clue. 11, 12, 13. That's 17. This is 16. So I haven't put in 14. I can see this can't be 14, so this has to be 14, but can't be, because you can't put 8 in it. What on earth have I got wrong here? Oh, how distressing as well, because it felt completely logical to that point. What have I got wrong there? Unless there's a way this digit... Let me just unwind a little bit. Because if that digit could be higher... Let's go back. Let's go back. I'm trying to watch very carefully for what... How did I get rid of 5 from... Let's just go... Ah, I did it there, look. There, that's where I did it. So I put 5 into that cell. And then I took it out. Now, why did I do that? And the only reason I'm asking that question is that if that was 5 and that would give me 15. And it would give me a latitude to create a cage that worked there. Why couldn't that be 5? It looks like I've really thought about it, doesn't it? I've gone. So what have I done? I've put 1, 2, 3, 4, 5 in. I've got rid of 2 from there, which is totally legitimate. Oh yes, I remember thinking about this cage. That all looks fine. And then I've put 5 in here and concluded that it couldn't be 5, and that must have been for some mathsy reason to do with that cage. What was that? I have no clue. I don't know is the answer to why I've done that. But I don't trust it at all. Let's just... Okay, so I think let's go from here and think about how to... I'm going to leave that 5 in, and I'm expecting this to be a 5 now. Otherwise, there's a much more difficult problem. But how do we make progress? Now, I managed to get 7 in the bottom row, didn't I? So the key to that is to ask where 7 goes in the bottom row and conclude it can't be there. And I can do that very easily. If you put 7 in these squares, this would add up to at least 21 without the 4th digit. And I know the top digit in purple is 21. Or the top cage in purple is 21. So 7 in the bottom row still goes here. Now let's hope that that still becomes an 8. This still becomes a 4, 6. But now we might have a way out of the trap that we laid for ourselves. This is now not 7. This is not 4 because it's got a 4 in its box. I've got a 1, 3, 5 triple in this column. So that becomes a 4, which means that's a 4 and that's a 6. This is still 8, which is what we expected. Now everything's a bit different now though, isn't it? This can't be a 1 because they would add up to 11, and I've got my 11 cage in red. So this either adds up to 13, which I suspect it can't do because it doesn't work, or it adds up to 15. If that's a 5... that's lovely. Okay, so that doesn't work. If that's a 5, these two cages add up to the same number. They both add up to 13. So that proves that's a 4, which is, I think, the same as we had before. So that gives us the 12. No, okay, we keep going with that. That's 8, that's 6. Which... But now we don't know what this is, and I'm very happy with that. I'm very comfortable not knowing what this is. Because, well, I mean, we could back into the deduction that we made before, because we could say, well, if that's a 3, we haven't put the 14 and 15 cage into red, and this could be neither a 14 nor a 15, so it would fail. That's quite a complicated look-aheady reason that I think I'd have only got that after staring at this for a long time. So let's just see if there's something simpler now. We've got all these extra digits in. Right, what about these digits? These have now got to be 1, 2, 3, and 4. This square's become a 5. That might do some things. That's a 5. That's a 2. I've not been looking for 3s. I've still got 2 opportunities for 3s in corners. Right. If this is 5, do we know what this is now? That's 15, isn't it? We know they're 15, so this is 20. So one of these cages is 19 and one of them is 21. But I thought before I managed to work out that 9 was in the right-hand cage. How on earth did I do that? I don't know. Don't know how I did that. Got the 20 cage. Sorry, I realise I'm sort of corpsing here as I think about this and try and understand. I've got an 8 here. Okay, so that gives me a 9 here and an 8 here. Does that help with this one? The answer is I haven't got a clue because I can't remember what's going on in yellow. Yellow has a 15 and a 13 cage. So that can't be a 5. Good grief. This is down to 1, 2 or 3. There's now a 5 for sure over here. And I think it's going to be there. Maybe that's the way to do it. If that's a 5, I've got 13 plus at least a 1, 2 pair. So this can't be 5. So the 5 in this row is now forced to be here. Because if this is 5, the minimum sum of this cage is 16, which is impossible. 16 and 17 have gone, and that's all the high reds that we've got left. So that does become 5, which is a change. That is not what we had last time. So therefore, we've now got 11, 12. We haven't got 13 and 14, and what's that? It can't be 14, that's got to be 13, and it's got to be 13 without using 9 or 8, so it's got to be a 6, 7 pair, and I can see the order, which means that's not 7, and that seems to have become a 7 in the top row. I've got a 1, 3 pair, so I've nearly got my 3 in the corner. I've got a 5 here, I've got a 5 there, and I've got, I've got a 1, 2, 3 triple. Okay. That's not 4. I've got a 1. I've got 1. This is not 2 because the 2 in this 1, 2, 3 triple is definitely in this domino. I've got a 1, 3 pair here, so I get a 2 here. So no. No. Okay. Nearly. Very nearly. Now remember what we said about these two dominoes. That adds up to 15. So that adds up to 15, and that tells me the order of the 7 and the 6. So this is now a 6-9 pair, and I know the order. So this is not a 6, and this is not a 9. I didn't do it that way before, did I, to get the 9 in here? But I've sort of elided on something different to get me to the same result. Not elided, alighted. That's what my brain wanted to say and failed. Okay, so now what? What on earth do we do now? We shall... Oh, come on. That digit and that digit are the same. No, I wanted to put that in the corner, because that digit is not that one. So we might have to colour these 1s and 3s, I think. Yeah, okay, so that digit is in one of those two, which means it's the same as that digit, same as this digit. It's in one of these two squares. We've got 20 here. So what did we need? We needed, yeah, we needed a 19 cage, and we needed a 21 cage. It's not obvious to me how we do this. That square's not 4 though, I can see that. So the 4 in this row is in this cage, along with some quite high digits. Seven in this box is in one of 2 places. Is that useful? I think maybe we've got to revisit. Do we have to revisit yellow? Yellow had 6 digits in it, didn't it? 15. Were we looking for 10 as the lowest digit in 11, I think? The lowest digit in yellow. I think it was 10, 11, 12, 13, 14, 15. So one of these is a 10, and we haven't found that yet. But that can't be a 9, so that is not a 1. Okay. Well, let's look at these squares then. 1, 3, 4. Oh, there's an 8 in here. That's going to be it. This is going to be it. Okay, because how big can this be? It must have a 1 in it, because we know there's an 8 in it looking at the row, and if it didn't have a 1 in it, it would add up to 15 and be the same as that one. So there is a 1 in here, which means that's not a 1. So it's either 1, 4, 8, which would add up to 13. I've had 13. I can't do that. So it's 1, 3, 8. There we go. That's 1, 3, 8. This has become a 4. And that's a 1, 3 pair, so that becomes a 2. So this is a 1, 3 pair, so that becomes a 2. So that gives me my 10 cage. So I've now got a 10 cage. I've got a 12 cage. Yeah, this can't be the 11 cage, look, because it would need another 2. So this must be the 11 cage, and that must be 4, 7. Good grief. And now that square, this will be the proof in the pudding. That has to be a 5, and that means we needed a 14 cage, and we did need a 14 cage. Perfect. So that's a 5. This is a 4, 7. Oh, come on. This must now be resolved, surely. How do you... If you can't do it like this, how do you do it? This is weird. These are 1, 3, 7 and 9 by virtue of the row. That can't be 7. That can't be 9. I don't believe it. Okay, so... that can't be 2. Oh, I see. Right, there's a 1, 3 pair in the bottom row, which gives me a 4 in the corner. Okay, so this is a 4, 2. That's useful. 4, 7, 8. Aha. Aha. So this is not... I just keep getting these 1s and 3s all over the place. But this cage, that's gorgeous, right. All of the even numbers I happen to know add up to 20. So we can't make that 20 because that adds up to 20. So that's got to be a 7, which gives me my 7, gives me my 9. This had to add up to, it can't add up to 16 because that only adds up to 13. So it's got to be a 1. That's got to be a 3. So we've got a 12, 13 and 14 cage here. Oh, this 1 is going to do some work with the... Yeah, it's going to do the 1s and the 3s, isn't it? Here we go. Here we go. No, it's just stopped again. Although that's a 3 now. And this 7 is doing the rest of it. 1, 9, 6. 6, 8, 1, 3, 3, 1, 8, 1, 3. There we go. Is that possibly correct? Oh my goodness, that was challenging like crazy, challenging a go-go. Star Origami, what a brilliant puzzle. There was a lot to think about there, and the way it all worked was absolutely fascinating. That you can force a unique solution from that rule set strikes me as something close to miraculous, a different sort of miracle to some of the puzzles we've been doing. And thank goodness for Sven's software that allows us to sort of unwind, because otherwise I'd never have been able to spot that there was a problem. Well, I might have suspected there was a problem here, but to unwind to that point and work out how the problem could be resolved would have been very challenging. That's just beautiful, isn't it? There's so many little cunning interactions. It's a quality puzzle. Serial killers indeed. Well, today we have I think proved, frankly, the 5-colour theorem. Let me know in the comments how you got on with this puzzle. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.